Hey everyone, this is H.R. Long. I'm in my Zoom meeting, so you can see the Earth instead of my bedroom. So that's pretty cool. I'm kind of popping in and out of existence, so try to ignore that, but that's kind of the point. So, I'm a PhD student in science, and I'm just going to show you how to do nonlinear regression in Microsoft Excel by the Chi-square goodness of fit optimization method. And just to double check to make sure that I'm recording. Yeah, I am. So I'm going to share my screen so you can see what I'm doing. Okay, so first of all, I have sort of data that fits a function, and I believe that function happens to be a hyperbolic function, which is actually the Michaelis-Menten enzyme kinetics function. And I'm going to estimate the parameters of that function using chi-squared test statistic of the dependent variable, which is the velocity of the reaction, and going to make it a local minimum. So in order to do this method, you have to have data, and you have to believe that it conforms to some kind of function, and then you estimate the parameters of that function with the solver algorithm, and such that the parameters of that function yield a local minimum in the chi-square test statistic. So this is basically nonlinear regression, which is a useful skill for, say, your career or your job or to impress people. So first of all, let's say that you have your data. So substrate concentration versus the velocity of a reaction, where, for example, the velocity of a reaction in Michaelis-Menten enzyme kinetics terms is a change in product formation with respect to time, or the depletion of substrate concentration with respect to time, or the maximum velocity times the substrate concentration divided by the quantity substrate concentration plus the Michaelis constant, which is Km. And so, for example, it's supposed to be that the Km is the substrate concentration at half maximum velocity, and the maximum velocity isn't usually reached in the experiment, but it's pretty close to the maximum velocity you observe. And so we're going to infer that with nonlinear regression. So, basically enzyme reacts with substrate to form an enzyme substrate complex and then finally release the product. So, we're going to predict the velocity. So, equal sign the corresponding substrate concentration times, first of all, we need to have terrible guesses of Km and Vmax to show how good the algorithm is. So 1 and 1. And we're going to predict the velocity by equal sign substrate concentration times the maximum velocity, and you have to fix this with F4 key. Then you're going to divide it by the substrate concentration plus the Michaelis constant Km, and you're going to fix that with F4, and then you're going to drag down this formula with this box here. So now this formula is used in all these corresponding substrate concentrations, as you can see. And so now you're going to fit this with sort of to chi-square test statistic, which is the total summation of the relative squared differences in the dependent variable, which happens to be velocity. And so we want this to be a local minimum. And so, for example, this sigma sign is a summation sign. Let's see, can I highlight it? Well, yeah, it's that weird Greek symbol. And then from index 1 to n, so basically all of your observations. So you would use this chi-square formula for any kind of formula just to fit the parameters. So equal sign and then observed velocity minus the predicted velocity squared. See the parentheses divided by the predicted velocity. And then see this box here, drag it all the way down, click and drag. And so there you got, your chi-squared. And so here's our function, which is just plotted as a curve as opposed to data points, but I plot the actual data as blue data points. So, now, we have our predicted velocities and our chi-squared. So we're going to get the test statistic, which is the total summation equals sum of all these chi-squared values. But here we got a divide by 0 error because the dependent variable here in y is a 0. So we're just going to ignore that because Otherwise, we can't calculate it, but we still have 10 observations. So equals some, there you go. So a huge total chi-squared test statistic, it's supposed to be close to 0 or a local minimum, but we're gonna make it a local minimum. So, basically, in order to do this now, you need to install the solver, solver app through Microsoft Excel. So I'm going to show you how to do that. So this is for optimizing parameters. So file, and then options, and then add-ins and analysis tool pack. See this here? Go and make sure this box for the solver algorithm is selected. I'm not sure what this other stuff is, but you need this box for solver algorithm. And then OK, and I already did that. So now the solver application or tool shows up under Data tab and Analyze. So click on this total summation chi-squared value, which you see is right here. Click on that and then go to Data and then select Solver. Now we're going to set the objective cell to be the total chi-squared cell, this one, G5, fixed with those dollar signs. And we're going to make it a minimum or a value of 0, but there's no negative values here, so we're just going to make it a minimum. And we're going to change the variable cells, see these, click this here, and select KM and Vmax. We're going to select those, and we're going to make those be the ones we're optimizing. And then we're going to use this GRG nonlinear method. This method here is for linear functions, and this one here is for sort of an evolutionary algorithm, which means you have to know the upper bounds for your data, and I don't. So we'll use a nonlinear function. And subject to the constraints, you can add them like this, or I already added them. So I just basically set the constraints such that these values are positive, because in no world should they be negative. So they're all greater than or equal to 0. You can also set them to be integers or whatever. And so there, we're just going to solve it, and we're going to fit it. And so we got a really good fit. We have a very low chi-squared value, which is close to 0, 0.1195. And you can see I plotted this. It looks good. So there you go. So let's see, how did I plot this? Let's see if I can remember. So like, select all this data, then insert sort of, let's see. Let's see, then insert a plot. I think I made a combo plot. So let's see, substrate concentration. Or no, wait. Yeah. And then observed velocities. I think I had those be scatter. Or no, wait, this isn't working. Right, so just select this data here, which is the raw data, and insert, let's see, a scatter plot. And then what I did was I selected the plot and I went to chart design under select data. And let's see, I added another legend, which corresponds to the predicted velocities. Or no, wait, I need to give it a name, which is predicted velocities, and using the same substrate concentrations and using the velocities, the predicted velocities, and then OK. And then they need to add a legend. And then to make that nice plot, I made like sort of, you click on the chart here and then go to chart design, and, or no, wait, you click on the chart here. You go to chart design, you change the chart type to say a combo, and you just make this scatter like this. And then you just make this, let's see, no secondary axis, and smooth line. And there you go. That's how I made the plot. And then you label your axes and stuff. So, you know, I just did it by the nonlinear regression method, but I'll also show you how you can do fit this kind of function by linearization. So you can actually linearize this type of function, which is velocity is all this stuff here, by inverting it, or 1 over everything, which gives you a Lineweaver-Burke plot, which is basically y is equal to mx plus b, where say m is km over v max, x is 1 over s, and b is 1 over v max. So to do that, basically it would just be equal sign 1 over the substrate concentration. And just like before, you just drag it all down. And then velocity is just equals 1 over the velocities you're given. And then like before, you just drag it all down. And then you can actually plot it, insert a scatter chart, and then you get divide by 0 error in one of the data points. So you just remove that data point. And it's easy to understand why you get divide by 0 error, because it's 1 over 0. So select the chart, chart design, select the data, click on the data, edit the data, and for the x values, just ignore the divide by 0 error, and for the y values, just ignore the divide by 0 error. Okay, wait. What? Something went wrong. Why is there only 1 point? Oh. Okay, this is awkward, but I'll fix it. Select the data. X values is everything but the divide by 0 error. And then y values is everything but the divide by 0 error. And now everything should be good. So there, it's all good. And then you can add a trend line. So Excel can actually fit a trend line, but it just so happens that you know, this one's linear. Again, r squared value, which is really good because it's close to 1. But if I were to try to fit a trend line, such as the trend lines available here in Excel, it wouldn't work for fitting to this. But if you invert it, it works. And that's just because I know some mathematics. So there you go, there's your trend line. And you can also get it with the Lanessa function, which I won't really go into too much. But here I've estimated all the parameters, including the sort of standard error in the slope and the, or standard deviation in the slope and the intercept, which is a pretty cool thing. So now the Vmax is simply the inverse of the y-intercept, which would just be 1 over the y-intercept, which turned out to be 0.0147. So 1 over that gets you 67.870, and then the km would just be the slope times the Vmax, so 0.0413 times the Vmax, which is 67.870, and I just computed that. And so 2.806 and 67.870, so it's only not showing all the points, so there you go. So here you actually see that we get pretty good estimates by linearization and then a linear regression of your data, or you can just do nonlinear regression. But actually the nonlinear regression estimate is better, because if we save these data points here, and then we replace them with let's see, what we got from the linear transformation and linear regression, then you get 2.806 and 67.870. So you see this number here is slightly bigger than this number here, meaning that the nonlinear regression is actually better. So there, you know, that's how you do nonlinear regression. So I think I might have stuttered a little bit. I'm sorry, but it wasn't that much. And so maybe it's like the 10th take or something. So in any case, you know, the basic summary is that if you have data that you think conforms to some function and you know what function it conforms to, then you can estimate the parameters using the solver extension from Microsoft Excel, such that the parameters of that function, which in this case were Km and Vmax, yield a local minimum or close to 0 and the chi-square test statistic, which is just basically the sum of all of the relative squared differences in your dependent variable, such that you get a local minimum in the chi-square test statistic, which is this right here. So there you go. Thank you. So have a nice day.